Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Building prototypes for streaming databases and seeing over the streams. He graduated earlier from IIT Madras with the President's of India Gold Medal, and in 1999, recently he has joined Stanford and is almost graduating at the end of this summer.
Thanks, man. In fact, I have my orals next Friday, so for Stanford. Yeah, this practice stop for my orals. So, good morning, everybody. I'm Arvind. I'm from the Stanford Info Lab, which until 15 days back went by the much more mundane name of Stanford TP Group. We have a new logo, new thing there. So I'll be talking about continuous queries over data streams, my work on that. And to start off with, what is a continuous query? So it is useful to define a continuous query by just considering, by contrasting it with what happens in a traditional query. In a traditional database, a query is a very passive entity. So it is issued by some higher level application. It operates over the snapshot of the database and it finds an answer. And once it returns the answer over the current snapshot, it ends. The important aspect out here is that when it's executing, at least logically, the image of the state of the database is invariant. It is fixed. It's not modified. It's possible that you have updates to the database, but these updates are not visible to the queries that are operating over the database. Okay, so this is a very simplified picture of what happens in a traditional system. So in contrast, a continuous query is an active entity. It is registered at some point in time, and it is active from the point it is registered. And what happens is when it is active, it observes the updates to the system, and it constructs and it outputs answers in response to these updates. And so to illustrate this schematically, you have updates that are arriving into the database, and this continuous CQ is active at all points, and it is outputting answers as the inputs arrive to the database. So to summarize, a CQ is a long-running active entity which operates over dynamic data, while your old one-time things are passive entities. They are short-lived and they work on static snapshots of database, right? So why are we interested in this? So it's interesting to look at continuous queries because they offer an interesting way to monitor and interact with a complex dynamic system, right? For example, you could monitor the states of the system, and whenever the system reaches an interesting state, you might want to generate an alert. Or you could maintain various kinds of statistics about the system. So in this case, the query is not producing an output, but it's at any point of time, it is maintaining some statistics about the system as a whole, and other applications or other continuous queries might ask about the present state of statistics from the system, right? So the important point is it remains active at all points and it maintains some kind of answer at all points. So as a very concrete example, the system that we are looking at, it could be a network of internet routers. So in this case, the state of the system is defined by all the network packets that are flowing across these routers, and we might want to monitor the state of these routers. And for example, we might want the continuous query to generate an alert if there is a significant reduction in the performance of the system as a whole. Or we might want the continuous query to report if there is some kind of a suspicious activity. For example, you might want it to automatically find out that there is a worm attack in the system, and you want it to report to some administrator that you have some kind of a suspicious activity. As another concrete example, you could have the system could be the stock exchange. And the state of the system is like the stream of stock tickers that are being generated by various users. And in this case, a user might be interested in various kinds of interesting patterns of stock so that he can react to he can react to these patterns by purchasing more stocks or selling off his or her stocks. So usually CQs work over a particular kind of data called as stream data. And actually there's no formal intuition, there's no formal specification of what is a stream and what is not a stream, but in general, stream data has all these features. One, it is generated by an external source and it is pushed onto you. And the continuous query has no control over the external source, which means that like it can only have one look over this data. You can do only one scan and you can't look at this data again and again, right? It is possible for you to store a snapshot or portion of the stream that you have looked at and access it later, but from the external source, you can only do one scan, right? And also because the external source that is generating the stream is not under your control, you can't control the rate at which the stream is arriving at you, and you can't control the sequence of the elements of the stream and so on. So it's basically outside your control. And also this stream is potentially unbounded. So basically there's no finite limit to the stream at the end of which you can output an answer and so on. So it's also useful to look at it's also useful to contrast the stream data with the traditional stored data, where the query processing application has complete control over how this data is laid out on the disk and how it's accessed when you're doing the actual processing.
You talk about arbitrary ones, but isn't a lot of the stream data sort of time-oriented? I mean, sort of the sequence about time-based.
So actually, what I meant by arbitrary sequences is that it's not possible for me to access the stream in a particular sequence. It is output to me from the external source in a particular order, and I can't affect the order. While if you have a relation that's on the disk, I can organize it in any way that I want and access it in any way that I want. I can order it by one attribute and access it and so on. I can't do this for streams, right? So as part of my thesis in Stanford, in the context of the stream project, I addressed the problem of how we can build a system that basically accepts declarative continuous queries over streams. And as part of this work, I addressed various research challenges that I've indicated here in the bullets. And I also was involved. I was one of the main implementers of the actual system, which is available as public software now, and it's also pretty efficient, and it processes up to 1 million stream tuples every second, and so on. So in this talk, I'll be focusing on these three aspects of my research, and all these three are related in the sense that they look at a particular set of CQs which are known as sliding window aggregates, right? Very briefly, what is a sliding window aggregate? So a sliding window aggregate applies some kind of window that slides over the stream, and over this window, at any point of time, it maintains an aggregate over the elements in the window. So that is a sliding window aggregate. So as you get more elements of the stream, the window slides over the stream, and you maintain the aggregate up to date, right? And why are we interested in sliding window aggregates? So aggregation is a fundamental operation that is useful for any kind of monitoring application. So they occur naturally very frequently in all kinds of monitoring applications. And also often for these monitoring applications, it is more important for you to look at recent data than something that occurred a month back. So and basically such a reference is indicated by using a sliding window, a window of recent elements that slides as the stream elements arrive, right? So out here you have examples of sliding window aggregates. So it's not important for you to understand all these examples in detail. I just have them here. I want to emphasize one point here. So the point is that sliding window aggregate is not an end in itself. It's an operation that can be used, like you can have multiple sliding window aggregations put together and form more interesting queries and so on. So for example, if you look at the very first example, so what you want to do is you have one sliding window over the last 5 minutes, and your computer can aggregate, which is the average over the last 5 minutes, and you have another sliding window which is the average over the last 1 hour. And you want to generate an alert whenever the very first average is larger than the second average by a certain fraction, right? In this talk, I'll be looking at sliding window aggregates in 3 different settings. In the very first settings, I'll consider what happens when you have a large number of sliding window aggregates, right? So when you have a large number of sliding window aggregates, it's not feasible for you to independently handle each one of them, just because every time you have a new input, you need to update the answers for each of the sliding window aggregates. So is it possible to somehow handle all of them is it possible to somehow share the resources that you're using to handle each one of these? Is it possible to share the resources across all the sliding window aggregates that have to maintain in some intelligent fashion? The second setting that I look at is what happens when the amount of memory that you have to handle this sliding window aggregates is limited, right? You can very easily argue that if you want to process a sliding window aggregate, it is necessary, if you want accurate answers, it is necessary for you to remember all the elements in the window, right? But assuming if you don't have memory to store all the elements, how can you do approximation, for example, in this setting? And the last setting is, in a certain sense, work in progress. That's work I'm working on right now. So what happens when the stream is not located in one location, but it is split across multiple nodes? So if you want to do an aggregation, you have to merge this information in some intelligent fashion before you can compute an aggregate. And the issue out here is you want to do this intelligently. You should not exchange, like you want to minimize the communication cost that's involved in computing this aggregate. So this is a pictorial representation of all these 3 settings. So in this setting, you have very large number of sliding window aggregates. The next setting, you have very limited memory, and you want to compute them. And then in the last setting, you have this stream which is split across multiple nodes, and you want to at least logically merge it and compute some kind of a sliding window aggregate. So outline of the rest of my talk, I'll start with some formal definitions, and then I will consider each of these 3 settings that I mentioned. And I will, in the end, I'll have a very brief summary of my other work before I conclude. So to start off with the formal definitions. So what's a stream? So in this talk, we'll assume a stream is just a sequence of elements because we are only computing aggregates, so we are not interested in any other attributes. But certain portions, this model is not correct, and I will indicate at that point what's the model of stream that I'm working with. What's a sliding window? We have like sliding windows. There are many variants of sliding window. The simplest variant has a fixed number of elements in the window. So which means that when you have a new element which enters the stream, the oldest element in the window, it leaves the window, right? And also I should mention the notation or general representation of streams. So in general, I'll be representing streams from left to right. The older elements are to your left and to my right, and the elements which will arrive in the future are indicated in this hash, and the elements which are already arrived are indicated in the orange color, right? So an illustration of how a sliding window, a fixed size sliding window operates. So you have new elements coming and those slides, right? But you also have other kinds of sliding windows. Like we could have a sliding window over the last 1 hour, which is the most common kind of sliding window, and you can't abstract the last 1 hour sliding window using a fixed size window. Just because it's possible that the elements the number of elements which you receive at this instant is larger than the elements that you received 1 hour earlier, which means that the actual number of elements in the window, it could vary. So what we have, like we can have an abstraction of this variable size sliding window. So in a variable size sliding window, at every instant, you could add a new element into the window, or you could also remove an old element from the window, but it's not necessary that you have to do this in a synchronous fashion. So as an illustration, you are adding, in this case, you just remove the oldest element, and the window is keeping shrinking, and so on and so forth, right? So this is the variable length sliding window. Actually, if you notice that the abstraction that I presented here is slightly more general than the abstraction that is required for time-based windows, right? It's because like if you have a whole bunch of elements which arrived at one instant, all the whole bunch of elements will be expired from the window at the same instant. While in this case, I'm considering something slightly more general. I'm allowing the adversary, if you will, to add elements at any point and remove elements whenever he wishes. So, but if you have algorithms for this model, it will work for the time window model, but not vice versa. And what is an output of a sliding window aggregate? So what we require is, like, if you want the algorithm that is that is handling the sliding window aggregates to maintain an answer at all points. But the notion of maintaining an answer is not well defined. So the only requirement that we have is, at any point you can ask the algorithm for the answer, and the algorithm should output the answer, right? So it can do anything that it wants. It can even just store the window, and it can output the answer from by computing from scratch when you ask for it. But the only issue is that the lookup cost for an answer is very high, but it's up to the algorithm to do whatever it wants. So in this case, so this is the external image of a sliding window aggregate. You have a window that is sliding, and at a certain point you have a lookup operation into this algorithm that is maintaining the sliding window, and you have to output the aggregate value at this instant for the window, right? So, and then you could have other kind of sliding, and then you'll have another lookup, you have to produce an answer. So I suppose everyone understands what's a stream, what's a sliding window. You have these two kinds of sliding windows: fixed size sliding window, variable size sliding window, and what is an answer for an aggregate over a sliding window, right?
So there are other models where an answer is output either periodically or every time the window moves. So is there any difference?
So actually the model that we have is slightly more general than that, because if you have a model where the answer is produced periodically, you could just have something that's asking the algorithm that's maintaining this answer periodically, and it works, right? So the model that we have is slightly more general than the model that you speak of.
Okay. But if I wanted to say that you still have to have some extra information to know when to produce the answer. If you have to ask, you should know when to ask, right? So isn't that part of the query in some form?
Yeah, it is part of the thing. But from implementation point of view, I think it is neat if we can separate out the part that asks for an answer from the part that maintains the answer, right? It's a neat separation. But it is possible that an implementation, it is possible that in this process where we are abstracting away the answer asking part to some other entity, we are actually losing information, right? For example, if the answer is required every 5 minutes, I can do something intelligent to exploit the fact that it's like after I answer something, I'm not going to have to answer for the next 5 minutes. It's possible. So by abstracting away that detail, we can't do that. But yeah, so.
So bottom line is, your requirement is that you need to be able to produce an answer at any point in time.
That's the bottom line.
Right.
Any other questions on the basic problem definition itself?
Well, so something that's pretty common is you got a particular sales coming in,
yeah,
and the sales have timestamps on them, and the timestamps that are on the sales are the time in which the sale was made.
Mm-hmm.
When it actually reaches your collector, they can be out of order by quite a bit.
That's right.
Right. Now, what I'd like to compute is some kind of low-pass filter on, showing what are my sales as a function of time, roll time, and I
That's
want
right.
some kind of low-pass smoothing of this.
Okay.
And I don't want to have, huge bursts whenever the collectors, drop out or catch up. So how do you provide, are you saying that you've got the basic building blocks to make this a simple calculation?
So if I understand your thing correctly, the issue there are two separate issues. The first issue is that the stream elements have their associated timestamp, which induces an ordering, and you want your computation to use that ordering instead of the order in which the elements arrive. Is that the deal?
I probably don't want to recompute this. I don't want to reorder the elements when I receive them because I don't have the memory to do that.
But he said some kind of approximation. You could do that like quantile estimation.
Sure. I still think you should be able to implement this without having to reorder.
And you could do like a group by, you probably want, let's say, within a week or month.
Yeah. Well, whatever.
So each one of those data sets, as you stream by, could be.
But also, then I don't want to have the lookup function shouldn't have a race condition in it, which is just whenever I happen to look it up, I want the low-pass filter should have has a well-defined notion of time. And the group by doesn't do very well either because that gives me a square window, and I don't want to use square windows for smoothing.
So, what exactly is your notion of low-pass filter? It should. What's the logic that's implemented by the low-pass filter?
Involved by a mask and downsampling.
I don't.
Yeah, maybe we can take it on.
Yeah, I can talk about this because I don't understand what is convolution properly. So, our very first setting, you have a large number of such sliding window aggregates, and you want to process them in an efficient manner, right? So the actual setting is as follows: you have one stream S, and you have sliding window aggregates over this stream S. So the very first question is, why do you restrict to the why do you assume that you just have one stream? The point is that you can't do anything intelligent across streams because you're looking at fundamentally different elements and values. So there's nothing intelligent that you can look across, you can perform across streams. You can't do any kind of resource sharing across different streams. So what we'll do is we'll focus on just one stream, and you have sliding window aggregates over the stream. And what is the input to the algorithm, Ravi?
You can't do some. Why can't you do value joins or something?
You can do joins, but in this case we are only looking at sliding window aggregates, right? And the aggregates over one stream, it need not be related in any way to aggregates over another stream. So there's no reason to handle multiple streams, right? So, and what is the input to the algorithm? The input is you have updates to the stream, you have new stream elements that are arriving, and you could have answer lookups for this various sliding window aggregates which are there. And I'm also assuming that the algorithm is aware of all the sliding window aggregates at the beginning of time. Got a question?
I'm just wondering what's the relationship between different operators, the same type of operators, the location of the sliding was different?
I will answer that in a minute. I have a picture that illustrates that one. Right? And then how do we evaluate the algorithms? So each algorithm has all these three, has one update cost, which is how long it requires when you have a new stream element. When it receives a new stream element, it has to modify its data structures in a certain way and update its data structures. So it has an update cost. It has a lookup cost. So when you look up for an answer, how long will it require to to output the answer? And then it also has a space requirement. How much space does it require, right? So we can compare multiple algorithms using all these three costs, right? And to answer your question, so you have this one stream, and each sliding window aggregate applies a window over the stream, and then it computes an aggregate, right? So, and then the important point I'm assuming is that, as I mentioned earlier, I'm assuming that all the sliding windows are over one stream. And in this slide, I'm also assuming that we just have one aggregate. It's not required. It's possible to do something intelligent across, for example, average and count, or average and sum. We can do some resource sharing, but to make things very simple, we'll assume that all the sliding window aggregates have just one aggregation function. So the only variation across different things is the windows itself, right? So which I've illustrated out here. So in the very first case, the window starts from the end of the stream, and it moves back to 7 elements and so on. And also, as you notice, the windows it's possible for sliding windows to start at history and move back. It's not necessary that for a sliding window to start from now and move back. So it's possible for you to have a window which consists of the last 15 elements starting from the 5th element from now, and so on, right? And now what happens is you could receive an input on the stream, and the algorithm has to update its whatever state that is maintained to accommodate this new input. And you could have a lookup for a particular thing, and the algorithm has to output the answer for this sliding window.
Does it change much your assumptions, or how does it help you to have a type of window where it looks back in history as opposed to eating the latest element that arrives? Do you make use of the fact that you know for these windows you know the next 2 or 3 values?
I don't make use of the fact. It's just that the application might require some window like that, right? I might want to do something intelligent, like I might want to compute some average for the last 1 hour and use it for the average and also compare it with the average from the last 1 hour to the last 2 hours and so on. It could be a function of application logic. But are you asking, is it possible to do something intelligent with?
What assumptions does it change the fact that the window is not from this time on until to sometime in the past?
It doesn't change any assumptions. It just is a window that starts from history and goes back history. Right? And just to complete the animation, you could have new elements and you have to keep maintaining and answer lookups. Right? So what are some obvious approaches, right? The obvious approaches is you could just, for every sliding window aggregate that you maintain, you could maintain the answer up to date. But what's the issue here? When you receive a new element, you have to visit each of the sliding window aggregates and you have to update the answer. And if you have just a huge number of them, say millions of them, it's just not going to scale if you have a very high input rate of streams. So for every stream, you have to update million counters or million values. It's not going to work. So which is why the update is very expensive. But then the lookup is cheap because I have the answer for each one at hand all the time. The other extreme is not to do any work when you have update. I just maintain the elements of the stream, and when I have a lookup, I just work out from scratch what the answer of this particular sliding window aggregate is. So this is possible, but now the update is very cheap. I can do it efficiently, but lookup, I need to recompute everything from scratch. So it's expensive, right? So the approaches that I will have is, it basically straddles, it is basically sitting in between these two extremes. So what I'll do is I'll maintain some kind of state which is not too expensive to maintain when you do updates, but then when you do lookup, I have done some work, so it'll basically make my lookups faster. So in this talk, I'll be spending some time with these two algorithms which I'll present, and I have other algorithms which you can find in my paper. Right? So the interesting aspect about the algorithms that I'll present is they make no assumption about the aggregation function itself. The only assumption that they make is that the aggregation function is algebraic or distributive, which at a very high level means that if I know the aggregate for a set of elements and the aggregate for another set of elements, I can compute the aggregate for this the union of these two sets by just looking at the aggregates, or so at a high level this is what they maintain, right? So the very first algorithm. So the very first algorithm is called B-Int, and it basically uses a particular kind of structure to maintain answers. So what I have out here, so I have this stream of elements out here, which are represented by these circles. And what I do is I identify certain intervals of the stream. So and these intervals are organized in various layers. At the lowest layer, I have intervals of length exactly 1, right? And at the next layer, I have intervals of length 2, and at the higher level, I have intervals of length 4, and so on. And for each interval, what I maintain is the aggregation value for all the elements which fall in that interval. So for example, for this interval, I maintain, if my aggregation is max, I maintain the max of all the elements which fall into that interval, right? So the only state that the algorithm maintains is the aggregations for all these intervals. Of course, it's not required for me to maintain aggregation for all possible intervals. What I do is I just maintain the aggregation for intervals which are active in certain sense. And these intervals are the intervals which lie in the last nmax elements. And what is nmax? Nmax is the oldest element that I have to remember to answer some sliding window aggregate. So this is nmax. So up to nmax values, I maintain such an I maintain the aggregation for all these special intervals. Got a question?
What kind of assumptions do you have on your aggregation function?
I assume that they are algebraic, which means that if I know the aggregation for one set and I know the aggregation for another set, I can compute the aggregation for the union of these two sets. So that's the only assumption that I make.
What is the assumption on the function that defines the windows? How do you know how big a window is? Supposing the window itself is data dependent.
I'm assuming these are fixed size windows, which means that they are specified. You can extend, I should have made earlier. So I'm assuming the windows are fixed size windows. So at the beginning, I know what's the length of each window is exactly. And you can extend it for time-based windows by modifying the algorithms here. But you got a question?
Yeah. Do you assume the window can fit in your memory, or?
So in this work, I'm assuming the window can fit in memory. I'll be talking about what happens when you can't fit in memory, about approximations. People have done a lot of work, and I have done some work, and I'll be talking about it later. Question?
Would it be more correct to say you think the aggregations must be additive?
Yeah.
Because you want to derive the high level from the
That's right.
immediate neighbor.
That's right.
So you can't do things like distinct counting.
Yeah, it can't be holistic, for example. You can't do median, for example, using this thing. Although so you can basically extend the approach that we use, the scheme for intervals that we have here, to do like you can have a specific algorithm that works for quantiles and medians as a special case, but it works only for quantiles. It's something that we do for quantiles, but I won't be talking about it in this talk.
That use something similar to
It uses something very,
use something similar to Jane's p-squared estimation approach.
I don't know about Jane's p-square estimation, but I can mention very fast what it does. So what it do is it still maintains these intervals, but within each interval it maintains a sorted list of the elements that fall in that interval. And what you can do is when you want to answer something, we can just look at the sorted list and compute the quantile, any quantile that you want by looking at this collection of sorted lists. But yeah, that's a high level thing.
The sorted list is the subset of the original list. You do a subsample.
Pardon?
You said that you maintain a sorted list of the samples.
So that is only for medians. It's not for all algorithms. For all these algorithms, what I do is I just maintain the aggregate for all the elements that fall in that interval. Right? For example, if your aggregation is max, what I do is I'll maintain the max for all the intervals which fall in that interval, all the elements which fall in that interval. I'll maintain the max for all the elements which fall in the other interval and so on. Right? So
right, max is different from quantile.
Yeah, so we had to have a very simple approach for quantiles. We can't generalize it. Right? And how do you answer queries? Sorry. And how do you answer things? I think most people might have realized. So if you want to answer a sliding window which has this interval at this point, what I do is I'll do the obvious thing. I'll express this sliding window as using the special intervals that I maintain. So in this case, I can express the sliding window here using all these intervals that I've already maintained. So if you want to do the max for this window, I can just look at the max for the interval here, the max for the interval here, the max for this interval, and the max for that interval. And the maximum value of all these maxes is a max for the entire interval. And it's not specific to max. It can do it for any algebraic aggregate, right? And how expensive is this? If the width of the sliding window is W, you can argue that you can always express such an interval using order log W small intervals, the special intervals that I maintain. So the lookup cost is basically order log W, because you need to look up order log. You need to look at order log W maxes if you're maintaining maxes and compute the max of this. So which means that this lookup cost is order log W. And how do you update this thing? It's very straightforward. When you have a new stream element, it's like you have to introduce all the special intervals that I maintain, so that I have this invariant that all the intervals in the last n max elements are present. So in this case, when I have this element, I need to add an interval which basically computes the aggregate for that element alone. And then I need to add an interval which contains the aggregate over the last two elements and so on. And we can also do it slightly more intelligently. If you want to compute an aggregate for a particular interval, if you compute it from scratch, it's very inefficient. What you can do is you can just look at the intervals at the next level, and you can just compute it from the intervals. So in this case, I'll be computing the aggregate for the last interval using the aggregates for these two intervals, and so on.
Shouldn't you go all the way up?
Yeah, I have to go all the way up.
I mean, shouldn't you all go all the way up at every moment?
No, it's not every moment. So this is what I'm illustrating, right? So in this moment, I need to go all the way up.
And what I'm saying is you're missing a common clue would be show me from some day to today.
Yeah, but even then it's not required for you to go. In this case, I don't need to go all the way up. It's sufficient for me to maintain the last guy. Right? Because if I have something that starts from now onwards and moves back, I'll add the aggregate. I'll use the aggregation for this interval. I'll use an aggregation for some other interval, and so on. So I'm not losing any information.
You can do it. I'm just saying it'd be more efficient at query time.
Oh, it could be more efficient at query time. Yeah, so that's possible.
So if I remember correctly, this is similar to this dyadic sketch, and recently
that's right. Yeah.
Some work based on that also.
Yeah. So this is not. So I'm not claiming that this is a data structure that I involved, that I discovered. So people have been using this in math theory. It's just that we have adapted it for this kind of things. So people have used dyadic sketches. Question?
For a lot of aggregates, of course, you should be able to compute running means or running maxes and independent of the size of the window, right? I mean, running means, for example. You should be able to do it, let's say the length of the stream is n and the window is w. I can compute running means in O of n independent of w using an obvious algorithm, right? You add the leading edge and drop the trailing edge.
Yes.
I can do the running means in time independent of w. So this one's taking log w. Of course, it's more general, maybe.
Yeah, I'm assuming that so the algorithm that you hear works for any distributive algorithm. For actually, I have an algorithm which works exactly as you pointed out, and it exploits the fact that you can subtract out values, and if you have the ability to subtract out values, you can do updates in order 1 and lookups in order 1. So that's perfectly true. So this is for a general case. I'm not. Yeah. You had a question, Amar? So the idea is that because for each interval, if you want to maintain the aggregate, you spend order 1 time computing the aggregate for that interval by looking at the aggregates for the intervals below you. And you can easily argue that because this structure is exponential, then at any point you will have order n max intervals that you have to maintain. And for each interval, you are spending order 1 times, so the amortized update cost is order 1 still. Although in the worst case, you might have to go all the way up to log n max levels. So in the worst case, the update cost is log n max, but in the amortized case, it's order 1. Okay. So to summarize, the algorithm that I presented has update cost order 1 amortized, and its lookup cost is order log w, where w is the width of the window, and it requires linear space, right? So in this case, if you observe that it is slightly expensive to do lookups, while you can do updates in order 1 time. But if you have a workload which is like in which updates are very rare, but you have lots of lookups, is it possible to have an algorithm that has order 1 lookup, but but possibly more expensive update cost? So actually, there is an algorithm which I will present. In this case, updates are more expensive. It's logarithmic in the maximum window size, but you can do lookup in order 1 time. So this is an algorithm. But even before I start off with this algorithm, I'll consider a very special instance of this algorithm. In this special instance, what happens is I'm assuming that all the windows that I have are approximately equal in length, in the width, right? So all the windows could be that I have, it could approximately around 100 elements. So in this case, what you can do is I have an algorithm which can perform lookups in order 1 time and updates in order 1 time, and it's also linear in space. So, and this algorithm is called L-Int, L for landmark, and I'll illustrate why it's called what's the algorithm. So out here you have the stream of elements as before, and all these elements will be arriving in the future. And in the stream, I identify certain location called as landmarks. And this L-Int also has, so, and this L-Int algorithm also has assumes that the windows are within a particular range, right? So let's assume that the maximum window width is W max, and we have a minimum window width which is known to the algorithm, right? And this algorithm, as I mentioned, it identifies special locations on the streams which are called as landmarks. And these landmarks are very fixed locations, and each landmark is shifted from the earlier landmarks by exactly W min. So which means that every W min locations you have a landmark. And around each landmark you have a whole bunch of intervals which are associated with this landmark. So along with this landmark, I have an interval of length 1 and an interval of length 2 which starts at the landmark, and an interval of length 3 and all the way up to the maximum width of the window starting at this landmark. And I also have an interval of length 1, length 2 which end at the landmark. So you have this entire set of intervals around this landmark. And for each landmark, we have its own collection of intervals, right? So I can represent this in some sense like this, right? So for we have all these intervals in this landmark, all the intervals that are in this landmark, and so on. And as before, for each interval that we maintain, we just compute the aggregation of all the elements which belong to that interval and maintain the aggregation, right? And as before, it's required for us to maintain intervals up to n max because we won't be looking at values. So how do we answer things using these intervals? So I have a window that I want to compute aggregate for, right? And I know that this window is between a minimum width and a maximum width. And because this window is above a particular, it's above minimum width, it has to intersect at least one landmark, right? So assume that it intersects the landmark that I've shown here. And what I do is I just look at the intervals that I've maintained around this landmark. Because this window is within, its maximum width is bounded, I can always express this window using a sum of two intervals, one interval which ends at the landmark and one interval which starts from the landmark. But I can always do this because I know that this width of the interval is bounded by the maximum width that I do. So I can just compute the aggregate for this interval by just looking at the aggregate for this interval and the aggregate for this interval. So which I can do lookups in order one time, right? So, and how do I do updates? So I can just compute. The updates is slightly more involved, but the easiest instance is illustrated here. When I have a new element that arrives, I need to compute the aggregation for the interval that I've indicated here, and I compute the aggregation for this interval using the element that just arrived and the aggregation for the earlier landmark, earlier interval as indicated here. And I can do this on and off, so forth. So you can do updates in order one time in this structure. But the only issue is that I'm assuming that the maximum window, the ratio of maximum window width to the minimum window width is a constant factor, but which is not always true. So how do we handle all these cases? It's very simple. So I just look at all the windows that I have, and I partition all the sliding window aggregates in such a way that within each partition the ratio is fixed. So I can just partition it to powers of 2, and I can assign each sliding window aggregation to one partition, and within each partition I can run this algorithm. So what happens in this case is that the updates now require, in the worst case, it might require log n max updates because I'm running log n max instances of the L-Int, the special case L-Int algorithm, but the lookup is still order 1, and the space also, there's an increase in space. So the space can go to n max log n max. Question?
So for lookup, the query window may not be perfectly aligned to the two windows you're maintaining, right? How do you handle that kind of case?
I'm not maintaining two windows, right?
I mean, do you return approximate answer?
No, this is exact answer. So in this case, it's not aligned to any window, any interval that I'm maintaining. But the only thing I'm asserting is that it intersects at least one of the landmarks. It has to intersect one of the landmarks because these landmarks are spaced W min apart, and this window is at least as big as W min. It intersects one of these landmarks, and after I identify the landmark that it intersects, I know that the maximum width of the window is less than W max. I have a value, which means that I can always express this using these two things, right? Because if you look at the earlier slide, I'm ensuring that the largest interval that is starting from the landmark is up to W max, and I know the interval for which I'm looking for the window is smaller than W max, which means that I can always do this. Right? So you can always answer correctly, Amar.
So every time you have a new element, the order 1 is the constant is the size of the minimum window, right, or the maximum window. So you have to update W max intervals.
No, you just need to update that one interval, right? Because I have computed the aggregate for all the earlier intervals. So in this case, when I have this new element, I just need to compute the aggregate for this interval, and I have the aggregate for this interval. I can do it. The only issue is what happens in this case. I need to compute the aggregate for all these intervals. In the worst case, which is why at this point, when I had this element, I had to compute the aggregate for this interval, up to n max W max intervals. But then in the amortized sense, it becomes order 1 because this is occurring very rare. Question?
Can interval span 2 landmarks or no?
A window span 2 landmarks, it's possible, right? Because the width of the window is W max, so I can intersect multiple landmarks, but it won't matter for me. I can use either of the landmarks to answer my query.
You only need to use one.
I need to use one.
So, but then if you're actually keeping the things for both the landmarks, don't you have to update both? So maybe 5 active landmarks here.
That's possible. But the point is that the number of active landmarks is constant because the ratio of the W max to W min is constant. So your update cost is still constant. Questions? So is this clear? So we can handle general. How much time do we have?
We have 20 minutes, 15 minutes.
Okay. So actually we have implemented all these things. So in a certain sense, experiments are not very interesting in this space because we have exact results, exact counts for all the algorithms that I have mentioned, but it still gives us an idea of how fast we can implement. And I should also mention one interesting point about the implementation itself. Because of this particular structure that we have, of the very first algorithm, that it's all the sizes of all the intervals are powers of 2, it admits a very efficient implementation because you can represent all the operations of splitting a window into these intervals using a gate level operations. So it can implement it really efficiently. So I have some results here. In this case, basically I compared the performance of our algorithm using the obvious approaches that I mentioned in the beginning. Right? The obvious approaches are I maintain the answer always up to date, and the other obvious approach is I don't maintain anything when I receive an update. I compute everything from scratch. So as expected, the performance of each one of I should say what the experimental setup is. So the experiment is what we do. We have a certain number of sliding window aggregates that we maintain. What we do is, and your input, as I mentioned earlier, it contains of updates to streams or lookups for answers. And basically what we did is we just varied the ratio of updates to lookups. In one extreme, you have lots and lots of updates, but very few lookups. The other extreme is you have a large number of lookups, but very few updates, right? So, and then what happens? So in this case, updates, if you have very few updates, the approach that maintains the answers up to date obviously performs very well because it's not required for it to update the answers very often. So and it can answer lookups very fast. But as the number of lookups increases, its performance falls exponentially. And the other extreme is the approach that's lazy. It maintains, it's not computing anything, which means that as the lookups increase, it's doing more and more work. So its performance also decreases exponentially when you have a large number of lookups. But when you have only updates, it does very well. And the approach that I mentioned here is very stable. It basically performs uniformly in the entire spectrum. And actually, its performance increases slightly as the number of updates increases just because its lookups are more costly than updates. So that's expected. Actually, I compared it against one earlier work, but I won't go into it because I need to describe what the other thing is. So I'll skip this part. Ming-Shing?
Just one question on the previous part. So there is this obvious trade-off between query and lookup cost, right? So do you consider adaptive algorithms in dynamically choosing one technique based on the current ratio?
No, at this point we are not considered, but yes, like it's possible if you observe the earlier algorithms, right? Basically they're not using any information about this actual sliding window aggregates that you have to maintain. It's possible that I need to maintain certain kinds of windows and not everything else. The algorithms basically answer everything that falls in this interval, and they're not using that information. We've worked on it for some time, but it's like because the windows are sliding, it's not easy to exploit the fact that I have windows of a particular form and things like that. So it's not, and yeah. So it's a very general thing. It's not even exploiting the information about the window distribution, and it's obviously not considering your adaptive approaches. But there's something you can do there. Question. So I will skip ahead into the next portion of the talk, in which I'm basically assuming if you want to compute a sliding window aggregate. So in this case, I'm just computing one sliding window aggregate. I'm not worried about resource sharing across multiple sliding window aggregate. But assume that if you want to compute one sliding window aggregate, obviously accurately, it's required for you to remember every element in the window. Why is this the case? Because when the window slides, I need to update the answer by expiring the element that went out of the window. So which means that I need to know all the elements in the window if you want to compute the answer, the aggregate accurately, right? But assume that I don't have enough memory to store the entire window. What can I do? Obviously, it's required for you to approximate. And so in this work, I'll consider how can you approximate the answer to a sliding window aggregate, but with much smaller memory. And I should mention that this is a very active area of research, and lots of people have worked on it, and I will point out at various points. But what we did is we have results for like specific forms of statistics, which are very important. And I'll also, so in this work, I'll consider very specific statistics. Like one of them is a median or quantile that you talked about. The other thing is like frequency counts. So what is frequency counts? I have a stream of elements, and I want to find out the elements whose frequency is above, say, 0.1 of the entire length of the stream or something like that. I want highly frequent elements who have a particular frequency. How can I find it? So that statistics is called frequency count statistics, right? And now we have a stream, and you want to maintain either frequency counts or quantiles over a sliding window of the stream. But now, because I can't store all the window in memory, I can approximate, and this approximation is specified by an approximation parameter epsilon. And again, the input is the update to a stream, so you can have new elements, and you can look up the answer, the approximate answer at any given point. In this particular setting, we'll be focusing mostly on space and will not concentrate so much on update and lookup cost, but I can talk about that offline if you're interested. So what is our contribution? We have algorithms which basically run in, like as I mentioned earlier, all the approximation has an epsilon, which is the relative error parameter. All our algorithm is linear in 1 by epsilon, and so basically they work for fixed size windows and variable size windows, and for both window classes we have a space requirement that goes like this. And I don't think there has been any work on frequency counts before our work. There was work on quantiles, computing approximate quantiles, but it is like quadratic in 1 by epsilon. If you observe that, if for example, if epsilon is 0.01, like what is 1 by epsilon square is like 10,000. So it is not good to have quadratic in 1 by epsilon. So ours is 100 versus 10,000. So it is like orders of magnitude reduction in space. And in this talk, I'll be mostly focusing on frequency counts, but all the ideas are essentially very similar. And in general, I think it's been observed that anything that works for frequency counts also works for quantiles because they have very similar properties. But it's an intuition that I got from this work. It's not very precise. But I also believe that an important contribution of this work, if you remember early, you had this multiple forms of sliding windows. One was a fixed size sliding window, which is mathematical but not very interesting. The other thing is variable size sliding window. And an output of this work is that we have a very general approach to look at any algorithm for fixed size sliding window which has a certain property, and automatically constructing an algorithm for variable size sliding window, right? Without modifying the algorithm for the fixed size sliding. It's using this algorithm as a black box. So I think this is an important contribution. Like when we wrote the paper, we didn't realize this, but so it's not published properly, but this is an important contribution of this work. So and if you use this approach, you can obtain much simpler algorithms than the earlier work for sum and count. To start off with, what is a frequency count? So we'll start off with exact frequency counts. Exact frequency counts is very simple. You have a bag of elements, and for each element you just find its frequency in the bag. So for all of you who are more comfortable with SQL than real math, so this is just select a count star from any relation, any bag, and I'm doing a group by on attribute A, right? So this is exact frequency counts. So what is approximate frequency counts? Approximate frequency counts has elements as before, and they're approximate counts. But this approximate count has a certain restriction. This approximate count, approximate frequency, has to be smaller than the exact frequency, but it can be smaller by at most epsilon m, where m is the number of elements in the bag that you're computing. So where m is the size of the input and epsilon is the specified error parameter that you want to satisfy. So you want an approximate count that is smaller than the actual count, but it's not smaller than by a large amount. So it's smaller by at most epsilon m elements, right? And also in the output, it's not required for you to to have all the elements in the output, it's okay for you to show elements whose approximate count is larger than 0. I'll illustrate that with an example. So as before, we have these elements, 20 elements, and assume that this epsilon error is 0.25, right? So the absolute error that we are allowed, epsilon times m, is 0.25 to 20, which is 5. So what does this mean? For each element, we need to have an approximate count, but this approximate count it must always be smaller than or equal to the actual count, but it can't be smaller than more than 5, right? So for element 1, its actual count is 7. It's okay for me to have an approximate count that is 3, and in which case the error is 4, right? So, and obviously this is not unique. I can have multiple answers, right? For the very first element, I can have an approximate count that's anywhere between 7 and 2, right? And it's also, you can't look at this font, but the point is, so for the other elements, it's not required for the other elements to be in the output because their approximate count is 0. So the output, it's just sufficient for it to contain all elements whose approximate frequencies or counts is larger than 0, right? So there's an illustration of another output for approximate counts. So in this case, you have an element 1. The output just contains of element 1 and 3 and their approximate counts. The intuition is that, one observation is that in any output for approximate counts, it is necessary for you to have these two elements, because it's not possible for you to make the approximate count of 1 be 0, because you'll be above the absolute error limit that is specified, right? So in general, if you look at approximate counts for any set of n elements, all elements in the original set with a frequency larger than epsilon times m must appear in the output. And for any other element, it's not required that it appears in the output, right? So which means that you can always have an output which is at most 1 by epsilon elements in size, right? And actually I should mention that the approximate frequency counts problem is a well-studied problem people have looked at earlier, and it's a well-known result which has been it's a well-known result that you can compute the approximate frequency count of size 1 by epsilon using space that is 1 by epsilon in just one pass over the input, right? And apparently it looks like this result is a very popular result. It was initially found in 82, and people have been finding it ever since multiple times, so including many people very recently. So, but of course the algorithm that I mentioned here is overrun. Like, you can still use it over a stream because it can do it in one pass, but you can't use it for a sliding window. For a sliding window, you have to expire elements from the window. So that's where the catch comes, right? So is the notion of a frequency count and approximate frequency count clear? So how do we get algorithms for frequency counts? For our case, where you have a sliding window, and this window is of length n, and n is known because we are looking at fixed size sliding window, and epsilon is known because the error parameter is specified, and this absolute error now is also fixed because n is fixed and epsilon is fixed, right? So to start off with, what is the issue in maintaining approximate answers in limited space, right? The issue is, as I mentioned earlier, when the window slides, you need to somehow expire the element that went out of the window. But if you remember all the elements, if you want to do this accurately, I have to remember all the elements, right? And my space just increases. I can't do it. So what people do is, instead of considering each element independently, they coalesce elements which occur next to each other into blocks, and they consider elements using basically they consider at the granularity of blocks, right? And all the algorithms which I know, which are in this space, which do some kind of an approximate statistic over sliding window, they maintain various kinds of blocks and expire elements in units of blocks, basically, right? And our approach is very similar, and all of you might recognize this thing. So we have a particular form of looking at this stream and splitting it into blocks. So, and it's exactly identical to what I mentioned earlier, except now at the smallest level, the blocks are not of length 1. If the blocks were of length 1, the space required is linear in the window size, which we don't want to do it. So again, these intervals are organized in multiple levels. At the smallest level, you have interval of a particular length, which I'll mention what the length is. At the next level, you will have intervals that are twice that length, and so on. And for each interval, what do we maintain now? So intuitively, for each interval, earlier we used to maintain the exact aggregate for that each interval. What we do now is we maintain some kind of an approximate information about the elements which fall into that interval, right? And I'll mention what the approximate information is. So for this interval, we maintain the approximate synopsis of all the elements which fall into that interval, right? And as before, at every point, it's not required for you to maintain all the intervals. It's only required for you to maintain intervals which are within the last n elements, right? So to illustrate this point, when you receive a new element, it's not required for you to maintain any information for the block that I've shown here, because all the elements are not within the last n elements. So we only maintain statistics or information for blocks which are active, which means that blocks, all of whose elements are within the last n elements, right? So and we have to maintain this structure as I've indicated. So at this point, we need to somehow maintain some approximate information for the block that I've shown here, right? And so on and so forth. And how do I how do I, at any point I want to compute the answer? Again, as before, I do it like I express the interval. In this case, I'm not computing the answer for any interval, because I want the answer for the last n elements. It's a fixed interval. But now I express this interval of last n elements using the smallest number of intervals, active intervals that I maintain. So in this case, I maintain intervals. I express this interval using all these intervals indicated below. I can't express it always. I can't always express it as a perfect union, because I'll have this elements in the end for which I'm not maintaining. I don't have intervals for, because the smallest level of blocks that I have is not 1, right? But it's okay. We are only doing approximate answers. So if the intervals, if the elements that I've ignored is small, it's not going to affect my approximation much. So we should ensure it's small enough to be within the approximation bounds, right? So in this case, if you want to compute the frequency count for the entire interval, you somehow just merge the information that I have stored along with these intervals and then compute the frequency counts. And I'll mention how we do it very soon. So now the actual details. The only details that I want is what is the length of the smallest block at the smallest level, because if I specify the length of the smallest block, all other blocks are specified. And basically, we maintain the length of the smallest block to be approximately epsilon times n. Epsilon is the parameter that I want, and n is the length of the sliding window. The intuition is that for frequency counts, I can afford to ignore epsilon times n elements here, but not more. And it's not required for you to remember to have blocks that are much smaller, right? And then, which means that because I have order epsilon times n, each block here is order epsilon times n, the number of blocks at the smallest level is 1 by epsilon, which means that the number of levels at which I have active blocks is logarithmic in 1 by epsilon, right? So the number of blocks here is 1 by epsilon blocks, and it reduces exponentially as you go up. So after I move up log 1 by epsilon levels, I don't have any active blocks, right? And the other detail that I have to mention is, what do I maintain along with each interval? Along with each interval, it's very simple. I just maintain the approximate frequency count for all the elements that fall into that interval, right? But the only issue is that I will not maintain epsilon approximate frequency counts. I'll maintain approximate frequency counts with varying values of epsilon's level. So within each level, the epsilon is fixed. So we'll have epsilon 0 for all the blocks with level 0, epsilon 1 for all the blocks with level 1, epsilon 2 for the blocks at level 2, and so on, right? and the issue, the invariant that we'll maintain here, the epsilon at the higher level is smaller. So epsilon 0 is the largest, which means that the approximation of the blocks at the smallest level is very, very high. It's not. It's a very inapproximate frequency count at each level. And as I move higher, it becomes accurate and accurate, right? So this is the basic invariant. And the actual error invariant is epsilon I for any level I. The epsilon into n, ni is the length of the interval at level I, right? So n0 is this width, n1 is this width, n2 is this width, right? I maintain the invariant that epsilon I times ni is a constant value. that's independent of the level, which essentially means that the absolute error for all the blocks across all the blocks that I maintain is invariant. It's a fixed value. What is varying is the epsilon, the actual relative error, and the ni value, the length of the blocks, right? And then I have to specify what is the merge operation. I have the frequency counts, approximate frequency counts for each of these levels. I need to compute the approximate frequency count at any point for the entire window. How do I do it? So as I mentioned earlier, I compute it by merging the approximate frequency counts that are sitting here. How do I merge it? It's very simple. So approximate frequency count is element and its approximate frequency count. And what I do is I just add up the approximate frequencies of each element. The intuition is that when you do this addition, the error also increases, but you can argue that the absolute error adds up. So if you look at one approximate frequency count and another approximate frequency count, the first one has an absolute error A1 and the next one has an absolute error A2. If you merge, as I've indicated before, as I've indicated here, the absolute error is A1 plus A2. And the intuition is indicated here. So you have exact frequency F1, approximate F1 hat, and F2 and F2 hat. And F1 hat is off from F1 by at most epsilon 1 times N1 times. F2 hat is off from F2 by at most epsilon 2 times N2 times. So if you just add up F1 and F2, the error is bounded by epsilon 1 N1 plus epsilon 2 N2. So that's the bound. So with this information, we have everything to analyze this data structure. So what is the error? I want to compute the frequency count for this entire interval of n elements. I have error because I have ignored some elements here, but it's order epsilon n, the width of the smallest block. I have ignored elements here. This again order epsilon n. I have some error that is obtained that is a result of the merge operation. And because this error adds up linearly, it's basically the number of merge operations that I perform into the error for each block. And as I mentioned earlier, the absolute error is fixed. It's invariant of the block, which is this value. And the number of merge operations is order log 1 by epsilon. So if you multiply these two things, the log 1 by epsilon cancels out. The error because of this merge operation is order epsilon n. And the error for the elements that I ignored is also order epsilon n. The overall error is also order epsilon n. So if you want to make this work exactly, it's required for you to plug in the constants. But this is the basic intuition. But of course we are interested in the space requirement. What is the space requirement for this entire data structure? So what we'll do is we'll consider the space requirement for each level and then add up the space requirements for all the levels, right? The space requirement at a certain level L is basically the space required to store the frequency count for each block in that level and the number of blocks in the level, right? And as I mentioned earlier, we know that the size of approximate frequency count for epsilon L approximate thing is 1 by epsilon L. The size of the approximate frequency count at each level, and the actual number of blocks is n. N is the fixed size window by the size of each block in that level, n by nl. So epsilon L into nl is the value that we know before. It's the absolute error for that level, which we know is epsilon n by log 1 by epsilon. Right, and this n cancels. So the space required for each block is also fixed. It's independent of the level. So it is 1 by epsilon into log 1 by epsilon. So which means that the space required for the entire structure is the space required for each level into the number of level, which is log 1 by epsilon. So it is 1 by epsilon log square 1 by epsilon. So it's all math. So you can just ignore it too. Okay, so the bottom line is you can do approximate frequency counts in space that is 1 by epsilon into log square 1 by epsilon. So I will very quickly consider variable size windows and then stop, right? So what happens in variable size windows is that you have error parameter which is fixed, but now the window size can vary. It can vary and it can vary in an adversarial fashion, right? And which also means that the absolute error it can also vary. We'll start off with the algorithm that we have here, right? It looks like it's because of the structure that we maintain, we can compute the statistics for any interval for any interval within the last n intervals. Because this structure it lets us So if you want to compute the answer for that interval here, we can still compute it. The only issue is the only error guarantee that this approach provides is that the absolute error is epsilon n, where n is the uppercase n. But for this interval alone, the relative error is not epsilon, but it's epsilon n times n, epsilon times uppercase n by lowercase n, which is not what we want. We want epsilon, right? So we can't use this structure, but we can still exploit this structure in a certain fashion. And the intuition is that if I refer to this entire structure as f epsilon comma n, f stands for fixed size windows, epsilon is the error parameter, n is the window size, right? So the observation is that if I maintain slightly more accurate structure, that is, if I maintain f epsilon by 2 comma n, I can basically compute epsilon approximate frequency size for all window sizes between n by 2 and n. So I have this limited variability as I'm right. So we can do this. And the basic idea is to have multiple such structures to compute the thing for a variable size windows. So what we do is we start off with n. N is the window size that small n is the window size that we have at this point. It can vary over time. And basically we compute this uppercase n in such a way that this small n is within a factor of 2 of uppercase n, right? So what we do is we maintain the fixed window structure for this uppercase n out here. So our structure for variable size windows is basically a collection of structures for the algorithm that I mentioned earlier for fixed size windows. So, but the only variation is the actual window size for these structures, right? At the very highest level, we have a window size of n. The next level, you have window size of n by 2, and so on, right? And now what happens when we have new elements? For example, when the elements are expired, so eventually we'll reach this point, in which case I can just ignore the highest level structure. I can just work with the structure. The only issue is what happens when you have new elements that are coming to the system. So at this point, it's required for me to construct the higher level thing. But the issue is like it's not required for me to construct the entire structure, because any of the lookups in the future will not involve any element that's sitting here. So what you can do is, so this is hand waving and the paper will have more details. We can construct a portion of f epsilon by 2 comma n from f epsilon by 2 n by 2. The intuition is that f epsilon by 2 n by 2 is a more accurate structure. So we should be able to construct the higher level structure from it. And basically we can extend these ideas to other kinds of fixed window algorithms, because the only information about f that I'm using is that you can use f to work out an answer for n by 2 to n. So we have this limited variability, and we should be able to construct a higher level structure from a lower level structure, and we can generalize this approach to get algorithms for any variable size windows. So I think I'll stop at this point. I have more stuff, but I don't want to go on forever.
Any questions?
Question?
In the landmark computation, it's after the landmark you have we know that we're increasing in size, right? We're keeping track to Stanford, and new element would compute the interval above. And that seems to be constant for me. But what about for the intervals for the landmark? How do you maintain it?
Yeah. So your question is, so what happens for all the intervals here, right? How do you compute them? So when I receive this element, I need to compute all of these things. So how do I compute it? I start by computing this interval, and then I compute this interval, this interval, this interval, and this interval. So each interval requires order 1 computation, but I need to perform all these computations at this instant. But the point is, such an instant won't occur every time. It occurs every once in a while. So it is still order 1 in an amortized sense. The worst case, it is order W max.
It's 1 in a while, or it's like off of the cases, right?
Huh?
It's a bit off of the points within the landmarks you need to compute.
Yeah, so it is basically the ratio of W max to W min, but that's a constant, so it's still amortized order 1.
One question. See, the approximate count problem in the error that you defined is the same as the traditional definition. I mean, your error is absolute in terms of number of elements that you're seeing into account.
The epsilon.
It's independent of the actual window size.
So let me.
Or is n the window size itself?
N is the window size. It's a fixed thing.
Yeah, that's fine.
Yeah. So. Raghav?
This is just one operation in the entire string query, continuous query, right?
Yeah.
So how does the error, what does it mean for the rest of the query? An approximate thing is there you work on the
Yeah. So.
an operator level is fine.
Yeah, I think that's a good question, and I don't have a good answer for it. But I think this is a thing that holds for all approximation work that people have done. So I don't think there is a good framework for looking at one approximate structure or synopsis and somehow merging it with the other approximation and having a good idea of like the approximation for the resulting plan or something like that. So I don't know of any work, and I don't have deep insights into that problem.
Another question. Suppose you have multiple lookup queries, right? And over a lot of windows, and you talked about how to answer one lookup query efficiently. But if I have multiple lookup queries over several windows, can you share some of the cost of looking up the answers for those?
Oh, are you referring to the first part of the talk or the second part?
Either one. I mean, suppose I have 1,000 windows that I have to answer, and you have a lookup query.
Yeah.
Give me all the 2,000.
So actually, that's a good question, right? So the issue, the assumption that I'm making is these lookups are independent. If the lookups are not independent, I can do something smart. So if I know that I'm computing the answer for A, B, C, D, it's possible for me to sequence the computation of these A, B, C, Ds in such a way that the computation for one will also benefit from the computation for another. So that is there, but I have not considered that way yet.
Thank you, Speaker.
I have a question on, as you mentioned,